Today we will solve the problem 5.5 of Griffith third edition in Introduction to Quantum Mechanics. The problem 5.5 consists of two parts. Now we will see the part A. Write down the Hamiltonian for two non-interacting identical particles. That is, here it is identical particle in infinite square well. Verify that fermion ground state given in example 5.1 is an eigen function of Hamiltonian H with the appropriate eigenvalue. Now the nth state wave function for infinite square well potential is equal to square root of 2 over a sine n by a multiplied by x. This is the wave function for nth state of infinite square well potential. Here it is given there are two non-interacting particles. So let us say the particle 1 is at state 1 and particle 2 is at state 2. So particle 1 is at the wave function for the particle is uh, you know 1 over square root 2. Of course, we have taken this square of the uh, normalization constant which is 2 pi a, because we are dealing with two non-interacting particles. The first one sine pi x1 over a is the wave function for the first particle with normalization constant square root of 2 pi a. So this can be written in the linear combination form 1 over square root 2 sine pi x x1 pi a sine 2 pi x 2 pi a. This is the particle 2 at the energy state 2, second state. Similar, since it's a fermion, we are writing this wave function in uh, linear combination with the negative sign. Negative sign is for fermion. If it is positive sign, it is boson. So here this is sine 2 pi x1 over a multiplied by sine pi x2 over a. Here, this is the wave function of particle 1 at the energy state 2. Here, particle 2 at the energy state 1. Here, it is vice versa. So, if you multiply this constant, 2 pi a is the square of the normalization constant, and this is 1 over square root 2. So this and this can be get cancelled. So this will become simply square root. So this will become square root 2 over a, and same the terms inside the bracket will come as it is. We have seen that wave function is psi is equal to square root of 2 pi 2 over a multiplied by these terms inside the bracket, that is sine pi x1 over a sine 2 pi x2 over a minus sine 2 x1 over a sine pi x2 over a. And now you differentiate the psi with respect to x1 twice. That is second order differentiation. So if you differentiate sin x, you will get cos x. Then pi a times the cos x. If you differentiate again cos x, you will get minus sin x. So which is again you will get 1 pi by a. So this will become minus pi by a squared sine n pi x1 a sine 2 pi x2 over a plus here same thing. If you differentiate first with respect to x, you will get 2x, and then if you differentiate again with respect to x1, you will get 2 pi over a whole square. Of course, you will get minus. Already there is one minus here. So that will become plus, and the remaining portion I am leaving as it is. Similarly, if you differentiate the wave function with respect to x2 twice, then this will be here x2 is 2 pi x2 over a. So when you differentiate this, you will get to 2 pi over a cos theta. If you differentiate the cos theta, then you will get to minus sine theta, and again this coefficient will come 2 pi a. So this will be minus 2 pi a whole square. Then the remaining term I am keeping as it is. Here we are differentiating with the x2. Apply the same rule. This will become minus pi by a whole square. So here already there is minus. So this will become plus. So remaining things are same. Now you add this. What will happen? The square root of 2 pi a is common. Now you take pi by a as common, because in that case you can take pi by a square as a common term. So you take minus pi by a whole square as a common factor. Then rest of the factor is here minus we have taken already out. So this will be sine pi x1 over a multiplied by sine 2 pi x2 over a. Uh, then you can take this red color bond, because in the red color bond only you have pi by a squared as a common, pi by a whole squared as a common factor. So you can take pi by a whole square as a common. Uh, so naturally, what will happen? Uh, Now you add this red color. That's what I have done. So that is square root of 2 over a. This sine pi x1 over a, and sine 2 pi x2 over a. Here, because I have taken minus outside, this will uh, become minus, because minus of minus will become plus. So I have changed this sign. So this will be minus sine 2 pi x x1 over a multiplied by sine pi x2 over a. You do the same thing for this blue color part. Here you take minus 2 pi over a whole square outside, because it's a common. Then this will become sine pi x1 over a multiplied by this factor. And here, as usual, we have taken minus outside. So this will be become minus. So here sine uh, 2 pi x1 a multiplied by sine pi x2 over a. See, I have taken this into two red color, sorry, two rectangular parts. Here, first rectangular box, you see this, compare this wave function and this one. So exactly this is nothing but the total wave function. So if you add these two, second order derivative of x1, x2, you will get this rectangular box is psi. So minus pi by a whole square psi. The second one is also psi. Of course, you have multiplicative factor minus 2 pi by a whole square. 2 pi by a whole square. So I am taking a minus outside. Then this will become uh, pi by a whole square plus 2 pi by a whole square psi. So this will be here 1 pi. So 1 square plus 2 square. Here you can take pi by a squared as common. So naturally pi squared a squared it will become. Here you have 1. 1 squared plus 2 squared is 4. 4 plus 1 5. 5 times 5 squared divided by a squared. Of course this minus I have taken. Multiplied by psi. So we got this one, that is sum up the second order derivative of psi with respect to x1 and x2 is equal to minus 5 times pi squared over a squared psi. Then according we can use the eigenvalue equation, that is minus h cross squared over 2m delta 2 psi over delta x. That is here x is x1 x2. So this is delta x1 uh, 2, here this is delta x2 power 2. So you will get this h cross squared. Here you already have 5 times h pi squared, so this h cross squared also will come, so this will become pi squared h cross squared. Already a squared is here, so this will become 2m a squared. This minus and this minus will get cancelled, so this will become plus 5 times pi squared h cross squared over 2m a squared psi. So here this is the minimum energy level. You know, when n is equal to 1, this is the energy level. This is initial energy, that is ground state energy, E1. So this eigenvalue is which we are calling according to eigenvalue equation is equal to E psi. Here E is equal to 5 times E1. So eigenvalue of this problem is 5 times the E1. Next, we will move on to the part B. Find the next two excited state beyond the one given in example. The wave function energies degeneracies for each of three cases distinguishable, identical boson, identical fermion. Here, before going into the detail of here since it's an identical particle, yeah, x1 and x2 are just a label. So even if you change x1 to x2, x2 to x1, nothing will happen. So this is the non-degenerate energy state. Phi E1 is non-degenerate. So with this in that mind, now we will go for distinguishable. This is indistinguishable. You cannot distinguish the particle, identical particle. So site in this case, site 2 that is first excited state. Site 2 is 2 over a sine 2 pi x1 over a. You multiply by sine 2 pi x2 over a. So use the same method. You take second order derivative. Naturally, this will become simply. You can remember that the n squared plus n squared. Always the total wave function is the product of two wave function. The wave function of two particles, the product of total wave function is product of two wave function. 1 minute. So this is product actually. Product up to wave total wave function. However, the total energy is sum of these. So here, previous case we have that is nx square, ny square, like it will come n this square and this square. This is n n squared plus n squared in this case. Energy is a sum of two energy levels. So this is 4 times E1. This is also another 4 times E1. If you multiple add 2, you will get 8 E1. So E22 is 8 E1. Uh, this is non-degenerate because the energy level is same. So though it is distinguishable, both will have same state. So naturally, energy will not change. So it is a non-degenerate case. Now we will continue our discussion on distinguishable. Now, in earlier case, both are having same energy, so it is non-degenerate. Now, let us say two distinguishable particle with a different energy state. First one is energy state 1, next one is 3. So the total wave function is product of two wave function, that is 2 pi a sine pi x1 a multiplied by sine uh, 3 pi x2 over a. Here also the energy, sum of the energies here, it is 1, n is equal to 1 squared plus 3 squared, which is 9, 1 plus 9, 10. So same is the case. If you interchange the energy state, that is particle 1 is at energy level 3 and particle 2 is at energy level 2. Remember that you can distinguish both particle 1 and 2. So this energy state is different because both are distinguishable. So, but and the what about the energy level? Here, first case n is equal to 3. So n square is 9. Next case n is 1. 9 plus 1, 10. So here in this case also 10E1. So at 10E1 energy state, we have two different states. So it is naturally degenerate. Then we will see the identical boson. Here is simple. We have to take second order derivative, then it will become with respect to x1, x2, then you will get the total energy. So I have done it for part A. Same thing, you redo it. So since I don't want to waste much of time on it, you can do the same thing. Whatever I have done in the part A, you do. That is, take second order partial derivative and add to in order to find the total energy, you will get same result. Then for identical boson, so identical boson, if psi 2 2 both will have same energy excited state second state. So 2 pi a sine 2 pi x1 over a sine 2 pi x2 over a. As usual, you do the second order derivative of psi with respect to x1 and x2. So you will get the total energy. You repeat the same thing what you have done in part A. Then U22 will be 8E1. It is very simple to take. Here it is 2, here it is 2. So 2 squared, 2 squared. That is 4 plus 4, 8E1. Now, uh, these both are having different state. Now, if both are having same state, sorry, these both are having same state, what will happen if both are having different state? So then in part A we have seen the same thing, but at that case identical fermion, so we got minus here. Since it's a boson, it's a symmetrical wave function is symmetrical one, so we have plus sign here. If it is fermion, then it will be a negative sign. That you have to keep it in your mind. These are the identical particles, so changing label will not affect your result. Here you can say, as usual, you take second order derivative for the wave function with respect to x1, x2. Here it is 1. First case it is 1. 1 square plus 3 square. So 1 plus 9, which is equal to 10E1. So E13. Changing label does not affect your result. So this is also non-degenerate. Then we will see how it will happen for fermion. Now the identical fermion, in the problem they asked the next two energy state. Two excited state. Now you take 1 and 3. So this is the wave function. This is wave function for state 1. That is n is equal to 1. N is equal to 3. This is for the second particle. First particle and second particle. Since it's a fermion, I used negative sign here. So here it is uh, particle 1 is at energy state 1, particle 2 is energy state 3. Here, vice versa. Particle 1 is at energy state 3 and particle 2 is at energy state 1. So here, these are the identical fermion, like identical boson, whether it is positive sign, negative sign. In part A, we have done. So just these are the label. You can take a X3 or X4 or X5, whatever may be. They are identical. You cannot distinguish the particle between 1 and 2. So here the total energy is, here you have 1 squared plus 3 squared, same. So 10 E1. So let us say if particle has one particle is at second energy state, another particle is at third energy state, then the wave function can be written like this. Since it's a fermion, there is a negative sign here. So first one is 2 pi x1 over A. Next one is 3 pi x2 over A. Now we are interchanging the particle. Then here you can see the total energy is 2 square. Here it is plus 3 square, which is equal to 4 plus 9, which is 13. I also want. So E23 is equal to 13 E1. This is a ground state energy. So here also we have to do that process. Second order, you take the second order partial derivative with respect to x1 and x2, you will get the total energy. So it's a very simple question. Um, so we have seen the energy eigenvalue of identical fermion also. Thank you very much for watching my video and supporting me continuously. Thank you very much.